Close your eyes for a second and just picture the voyage to Mars.
Okay.
We always imagine that perfect, dramatic launch, the engines roaring, the machine just leaving Earth behind.
Big moment, yeah. The liftoff.
Exactly. But that moment, that only lasts for a few minutes. That's just the overture. The real terror, I think, starts once you're actually in deep space.
That's absolutely right. The middle part of the journey, the cruising phase, that's the terrifying part that nobody ever puts on a movie poster.
Right. Because once you clear the protective bubble of Earth's magnetosphere and you're truly out there, in the void, the clock just starts ticking against the crew.
And it's ticking fast.
Every day, every single hour, you are exposed to this relentless, high-energy cosmic radiation.
And this isn't like a sunburn. This radiation, it doesn't just pass through you. It's actively damaging your DNA.
It accelerates bone density loss. It dramatically increases your lifetime risk of cancer. It's brutal.
We can talk all we want about Mars colonization, but you just can't escape the reality that getting there slowly is lethal.
Our current chemical rockets they're marvels of engineering for sure.
Oh, absolutely.
But they still mean a voyage of what, 6 to 9 months one way?
Yeah, and that duration is just far too long for a crew to endure safely, even with the best shielding you can imagine. You have to shrink that timeline.
So humanity needs a shortcut. We need what feels like an impossible promise from science.
A cheat code.
Exactly. And that promise is a vehicle that could potentially cut that health-crippling trip time in half.
Imagine that. Reaching the red planet in maybe 100 to 150 days.
It's a game changer for human health.
And that's just the near-term goal.
Mm-hmm.
I mean, the technologies being researched right now are chasing something far more extreme.
Oh, yeah.
We're talking about a spacecraft that could potentially reach sustained speeds of 500,000 miles per hour.
500,000 miles per hour. That's just a number that doesn't compute.
That's staggering.
And that speed goal immediately tells you we're talking about a completely different game. We're not just, optimizing the existing chemical combustion systems with lighter alloys or slightly better nozzles.
No, you're fundamentally changing the energy source itself. That's the mystery build we are diving into today.
Huh?
How do you actually achieve that?
Because we are done relying on chemical bonds.
We have to be. We're talking about harnessing the power that fuels the sun, or at least the power derived from that same process, to push heavy cargo, and eventually humans, across the solar system with unprecedented efficiency.
Okay, let's unpack this. We've been given a massive stack of sources on the history, the staggering failures, and the kind of astonishing comeback of nuclear-powered propulsion systems.
It's a real roller coaster of a story.
And we are going to explore the two main rival technologies that are fighting right now to redefine our cosmic speed limit: nuclear thermal propulsion and nuclear electric propulsion.
And crucially, we're going to dive deep into the massive geopolitical competition, what Russia and China are doing, and this unexpected financial twist that just killed the biggest American nuclear rocket program.
It just completely shifted the entire focus of the space race.
It did. It's a story where the future of deep space travel relies on economics and, geopolitics just as much as it relies on physics.
Let's start with the villain of our story. And it's ironic because it's the technology that got us into space in the first place.
The chemical rocket.
Exactly. It's fantastic, but it's running into a physical wall.
It is pure elegance, but it's also brute force.
Yeah.
And the problem is that the rocket is fundamentally limited by the energy that's stored in chemical bonds.
Right.
So when you combine, say, liquid oxygen and liquid hydrogen, LOX-LH2, you get one of the highest possible efficiencies you can achieve by just burning fuel.
And that efficiency, it's measured by something engineers call specific impulse, or ISP.
Right, ISP.
So for those of us who haven't spent time around rocket labs, what does that measurement actually tell us?
Specific impulse is essentially a measure of how efficiently a rocket engine uses its propellant. Think of it like miles per gallon for your car.
Okay, that makes sense.
Or maybe the thrust duration you get per pound of fuel. The higher the number, the more punch or impulse you get out of a fixed mass of propellant. This is the holy grail for space travel.
And the chemical rocket, even the most advanced ones, they've kind of hit a ceiling here.
They absolutely have. The very best chemical rockets, like the workhorse RL-10, they tap out around 450 seconds of Iowa's door.
And that's it. That's the limit.
That is a physical thermodynamic ceiling. It's determined by the hottest temperature and the fastest exhaust velocity you can get through a chemical reaction. You just can't burn LOX and liquid hydrogen any hotter than it already burns.
And this 450-second ceiling leads us directly into the tyranny of Tsiolkovsky's rocket equation. That equation is just the nemesis of all deep space planners.
It is the brutal, unforgiving math of rocketry.
Yeah. So simplified, what does it say?
Simplified, it tells you that to achieve a desired velocity change, or delta V, the relationship between your final mass and your initial mass is exponential.
Meaning to go just a little bit farther or faster.
The weight of the fuel you need increases exponentially.
It's like compounding interest, but for failure. You need a little extra speed, so you add a ton of fuel. But
adding that fuel means you now need an even bigger rocket just to lift the fuel you just added.
You're stuck in this vicious circle.
Precisely. To do a mission like a Mars transfer orbit using chemical propulsion, the vast majority, we're talking 85 to 90% of your launch mass has to be propellant.
That's insane.
It is. It means you can carry almost no useful cargo, no crew habitat, certainly no spare parts. You end up launching rockets just to carry the fuel for the next stage of the rocket. It's an unsustainable logistical nightmare for deep space.
So we have to bypass that exponential curve entirely. We need a hack.
And that brings us to the ultimate energy density hack: nuclear power.
This is why it's been the dream since the 50s. Right?
It is. The shift from relying on chemical bonds to relying on nuclear fission is a complete game changer. Fission offers approximately 1 million times more energy density per unit mass than chemical fuel.
1 million times.
That completely sidesteps Tsiolkovsky's equation. It means for the same mission, you need vastly less propellant mass.
I saw one comparison that just stuck with me. A gummy bear-sized amount of uranium is supposedly the energetic equivalent of 500 barrels of oil. Or, get this, the entire upper stages of multiple massive space launch system rockets combined.
That's the difference between driving a scooter and powering a small city. That is the potential.
But if this technology is so revolutionary, why haven't we been doing this for 50 years?
That brings us to the ghosts of the past. The historical curse of nuclear propulsion.
It's a technology that has been promised since the 1950s, only to be stalled by budget cuts, political shifts, or safety concerns.
And the sheer ambition of some of these early projects is just hard to believe even today.
You mean like Project Orion?
The wildest one has to be Project Orion,
Yeah.
From the 50s and 60s. This was the classic big swing, studied by legendary physicists like Freeman Dyson.
And the concept was not elegant.
It was brutal and terrifying. The idea was to detonate nuclear explosions behind a massive spacecraft and ride the resulting blast waves for propulsion.
Wait. You're kidding. They wanted to propel a spaceship by literally dropping tactical nuclear bombs one after the other behind it.
That was the idea, yeah.
And they thought this was a good idea.
That was the idea. The impulse from each explosion would strike a giant resilient pusher plate mounted on the back of the spacecraft, pushing it forward.
That's unbelievable.
It was designed to send massive missions, think 100-ton payloads, across the solar system quickly. The engineering challenge was building a shock absorber strong enough to protect the crew from the sudden, repeated acceleration.
I'm sure the main issue was something else.
Well, yeah. The main issue was policy. Ultimately, the 1963 Partial Test Ban Treaty, which banned nuclear detonations in space, killed it.
Mercifully, I think. But the U.S. got much closer with thermal technology, right? Something a bit more controlled.
They did, and this is where the serious engineering began. It started with Project Rover in 1955 and its successor, NERVA.
NERVA, the nuclear engine for rocket vehicle application.
A huge joint effort between NASA and the Atomic Energy Commission. It was aimed at developing a nuclear thermal rocket for deep space missions, specifically Mars transit.
And potentially as an upper stage for the later Apollo missions, right?
That was the hope. And the sources confirm NERVA wasn't just hypothetical. They built and tested actual hardware.
So it worked.
It was a wildly successful proof of concept. Between 1959 and 1972, the program successfully developed and ground-tested several nuclear reactors designed to be integrated directly into a rocket engine.
And what did the tests show?
They showed that the physics worked perfectly. They could generate heat far exceeding any chemical reaction, achieving icy values in the high 800s.
So double the efficiency of chemical rockets.
Exactly. They proved the engine could start up, operate at full power, and shut down safely.
So the technology was proven in the lab, but the political will just vanished.
That's it. Despite the engineering success, the program was canceled in 1973. It was a casualty of the post-Apollo budgetary contraction and, shifting priorities.
It was ready for flight, but funding was withdrawn before a single engine ever flew.
It's one of the great what-ifs in space history.
And even the small programs that did make it to orbit had a short, frustrating lifespan.
You're thinking about SNAP-10A, Systems for Nuclear Auxiliary Power.
The only U.S. nuclear reactor ever actually launched into Earth orbit.
It flew in 1965. It was designed to generate about half a kilowatt of electric power. Very low, but a crucial step toward proving space reactor technology.
And how long did that little reactor last?
Only 43 days.
Oh, wow.
And here is the profound irony that just echoes through all nuclear space history. It shut down, not because the nuclear reactor failed.
Let me guess, a non-nuclear component.
A non-nuclear component, specifically a conventional voltage regulator. The nuclear part worked flawlessly, but a piece of standard electronics just failed.
And they knew the core could last longer.
They had an identical unit ground-tested for over 10,000 hours, proving the longevity of the reactor core itself.
It's the constant, infuriating story of space innovation. The hardest part works perfectly, but the simplest, easiest part breaks.
So the key takeaway here is that since the 1950s, the underlying nuclear propulsion technology has existed.
But it keeps getting stopped by this combination of shifting political tides, budget cuts, and complexity integration, especially of those non-nuclear support systems.
Fast forward to today. After decades of dormancy, the nuclear quest is back on, but it has splintered into two fundamentally different approaches to using that massive energy density.
It's the difference between building a drag racer and building an ocean liner.
That's a great way to put it.
Okay, so let's look at the drag racer first. Nuclear Thermal Propulsion, or NTP.
This is the direct approach, the spiritual successor to NERVA, and it's the one that promises the fastest trips for humans.
So how does it work?
The core idea of NTP is elegant. You take a working fluid, the propellant, and you heat it to insane temperatures using nuclear fission. Then you shoot the resulting superheated gas out the back end of a rocket nozzle to create thrust.
Okay, let's talk about the physics and the material science of that process, because it sounds like an absolute engineering nightmare in terms of temperature management.
It is.
What's the working fluid and how hot are we talking?
The propellant is almost always cryogenic liquid hydrogen, LH2. We're talking about a substance that is bone-achingly cold, around minus 420 degrees Fahrenheit.
Okay.
The reactor core, fueled by solid uranium, acts as a heat exchanger, forcing that liquid hydrogen through channels in the core.
So you're taking propellant that is barely above absolute zero and forcing it through a nuclear reactor that's instantly running white hot?
Uh-huh.
That sounds like a catastrophic recipe for thermal shock.
It is the ultimate test of material science. You have to take that liquid hydrogen and heat it instantly up to about 2,700 Kelvin.
What's that in Fahrenheit?
About 4,400 degrees Fahrenheit. And to give you a reference, a typical terrestrial nuclear power plant runs around 600 Kelvin.
So you're operating at temperatures that are nearly the melting points of structural metals.
Right. That's why the earlier analogy was not just cooking instant noodles in boiling water, but throwing them into the sun.
The speed of the heat transfer required and the ability of the reactor materials to withstand that thermal cycling, it's just astonishing.
It is. The fuel elements can't be standard metals. They have to be ceramics or composite materials like graphite or carbide-based compounds that are highly resistant to corrosion from the superheated hydrogen gas and that thermal stress.
And the whole thing has to start up in seconds.
The entire reactor startup needs to go from 0 to full power in as little as 60 seconds to provide the thrust needed for a trans-Mars injection burn.
Wow.
But if they pull this off, the performance is double that of chemical rockets. You're hitting an IS of 850, 900 plus seconds. That's the technology that makes the 100-day Mars trip feasible.
And there are even advanced theoretical concepts trying to push that efficiency envelope even further, like the centrifugal nuclear thermal rocket, CNTR.
Now you're talking pure sci-fi.
What's the idea there?
Instead of using solid fuel rods, the CNTR design proposes using liquid uranium fuel contained within a rotating cylinder.
Liquid uranium at thousands of degrees.
Precisely. The centrifugal force keeps the liquid uranium plasma contained in the core, maximizing the fission reaction.
Why do that?
The goal is to maximize the surface area for heat exchange and achieve even higher temperatures, potentially doubling the previous NTP designs well over 1,000 seconds.
But the risk must be monumental.
Oh, yeah. Containing a supercritical, high-speed, high-temperature liquid fuel is a huge engineering challenge, but the potential payoff is enormous. This is the kind of cutting-edge research China, for example, is heavily pursuing.
Okay, so NTP is the sprinter, high thrust, high acceleration, fast travel time.
Right.
Now let's look at the marathon runner, Nuclear Electric Propulsion, or NEP. This is the slow burn, the relentless push.
This is the completely different path. It trades acceleration for efficiency. With NEP, the nuclear reactor doesn't generate heat for direct thrust.
So what does it do?
Instead, the reactor generates heat. That heat is converted into electricity. We're talking megawatt-class power. And that electricity powers incredibly high-efficiency electric thrusters, like ion or Hall thrusters.
So NEP provides almost no immediate push. It gently nudges the spacecraft, but continuously for months or even years.
Exactly. The thrust is incredibly low. You could balance the entire output of an NEP system on your hand.
So it can't launch from Earth.
No way.
All right.
But once it's in orbit, it is the definition of propellant efficiency. We are talking about specific impulses ranging from 2,000 all the way up to 15,000 seconds.
Whoa.
It is the ultimate space tug. It's ideal for moving heavy cargo and large modular missions over vast distances, slowly gaining incredible final velocities.
This reminds me of Project Prometheus and GMO, the Jupiter Icy Moons Orbiter from the mid-2000s. They were trying an NEP system then, weren't they?
They were. Project Prometheus from 2003 to 2005 was an early attempt to develop an integrated MW-class NEP system.
But it stalled out. Why?
It stalled out due to what we call the 6 subsystem headache.
The 6 subsystem headache.
Yeah. That system requires integrating 6 highly complex interdependent systems: the reactor, the shielding, the power conversion, power management, heat rejection, and the electric thrusters.
That complexity is the Achilles heel of NEP. It sounds like trying to build 6 separate specialized machines and then making sure they all work perfectly together in a zero-fault environment.
That's a perfect analogy.
Okay.
And let's just drill into 2 of those subsystems that illustrate the immense scale-up required. First, power conversion.
Right.
SNEP-10A use static converters. They're simple, but they don't scale to megawatt levels efficiently. To get that kind of power, you need to shift to dynamic systems, like the closed Brayton cycle.
Okay, what does the closed Brayton cycle do, in simple terms?
Simply put, it's a tiny power plant turbine in space. It uses a high-speed gas, Luke-like helium, or xenon heated by the reactor. That gas spins a turbine hooked to a generator, creating megawatt levels of electricity.
But that sounds way more complicated mechanically.
It's much more thermally efficient, but it introduces massive mechanical complexity, high-speed rotating machinery that has to run flawlessly for years on end.
And once you have that electricity, you need the infrastructure to use it. That's the PMAD you mentioned, power management and distribution.
That's the electrical grid of the entire spacecraft. It takes the raw electricity from the Brayton converter and distributes it at the correct high voltage and current to dozens of electric thrusters.
And the thrusters themselves are a challenge.
Well, yeah. Current flight-qualified electric thrusters max out around 6.9 kilowatts. To hit the megawatt level needed for logistics, you either need thrusters that are an order of magnitude more powerful, or you need 50 to 100 of these smaller thrusters working together flawlessly.
And managing all that power is a massive, untested risk.
Huge risk.
Yeah.
Especially in a high radiation environment.
Okay, but the biggest engineering hurdle, the one that truly feels counterintuitive in space, has to be heat management, the radiator problem.
Mm-hmm.
If you're generating megawatts of power, you're also generating megawatts of waste heat. Where does all that heat go in a vacuum?
This is the massive paradox of space power. You can only shed heat through radiation.
Okay.
And that means the heat dissipated is proportional to the radiator's surface area and the fourth power of its temperature. Since space temperatures are low and our materials can only handle so much heat, you need a staggering amount of surface area.
So for these megawatt-class systems...
The heat rejection subsystem, the radiator, is actually the single largest and heaviest component of the entire spacecraft.
So if you want high power, you end up needing these massive, fragile, football field-sized wings.
Exactly.
And that's impossible to fit into any existing rocket fairing.
Exactly, which is why NASA is tackling this head-on with the RMRVL project.
RRVL, Modular Assembled Radiators for Nuclear Electric Propulsion Vehicles. That's a great name.
And it sounds like a perfect solution to the fairing limitation. The genius idea is acknowledging the limitation of terrestrial launch vehicles. The plan is to launch the radiator panels as modular pieces.
Like a giant space IKEA set.
Sort of, yeah.
Yeah.
Possibly stored as unrolled sheets, and then you use autonomous robots to assemble them in space.
Wow.
You solve the size constraint and allow engineers to build the massive kilometer-scale radiator arrays necessary to shed that megawatt-scale heat. It's a solution that fuses robotics, in-space assembly, and nuclear power into one coherent vision.
So the narrative of nuclear propulsion was set up as this great technological rivalry, right? You have NTP, the sprinter, trying to get humans to Mars quickly.
And NEP, the marathon runner, working on deep space logistics.
And then 2025 hit, and we saw this massive, strategically decisive shift in priorities that just fundamentally changed the space race.
We saw the stunning and, I think, highly controversial cancellation of the flagship NTP program, DRACO.
DRACO, the demonstration rocket for agile cislunar operations. This was supposed to be the realization of the NERVA dream.
It was a joint DARPA and NASA effort, massive contracts awarded to Lockheed Martin and BWXT, aiming for an uncrewed flight test of the NTP engine in 2027.
It was a great leap forward, and then in mid-2025, DARPA just pulled the plug.
It was a dramatic strategic reveal, and the official reason for the cancellation was cited as a declining return on investment.
This is the moment where economics killed physics.
It really is.
This is what we call the Starship effect, right? The changing economics of getting stuff into orbit completely reset the value proposition of nuclear propulsion.
Exactly. The core benefit of NTP was its high efficiency, its ability to save propellant mass. When launch costs were incredibly high, saving mass was paramount because every kilogram of mass saved meant millions of dollars saved at launch.
But now,
with commercial launch providers offering fully reusable heavy-lift vehicles like SpaceX Starship, launch costs are dropping dramatically, far faster than anyone anticipated.
so the argument just flipped. Why spend billions perfecting an exotic, high-risk nuclear thermal engine?
When you can just launch twice the amount of chemical fuel for cheaper on a commercially available vehicle.
It's a no-brainer from a budget perspective.
Exactly. The mass-saving benefits of NTP no longer justified its massive R&D costs or its lower technology readiness level, its TRL.
Explain that, the TRL part.
You have to consider that when DRACO was canceled, the NTP engine itself had only reached a TRL of maybe 3 or 4 points. It existed as components in ground tests.
Okay.
Meanwhile, reusable chemical rockets were becoming operational, and NEP systems were benefiting from decades of successful ion thruster operations, giving them a much higher TRL on key components.
So it's the ultimate disruption. A private company's economic efficiency accidentally decapitated the government's flagship deep space propulsion program.
And it forced a complete strategic reset.
And that reset led the Department of Defense to pivot immediately.
They weren't looking for fast human transit anymore. They were focusing entirely on power and mobility for military satellites, which is the sweet spot of NEP.
And that brings us to Jetson Joint Emergent Technology supplying on-orbit nuclear power.
This is the military's definitive response to the DRACO failure. It's the next phase of the U.S. nuclear space program.
So AFRL and the Space Force just shifted focus entirely.
To using fission reactors to provide sustained high-power electricity to military satellites, rather than direct thrust. Lockheed Martin, Westinghouse, Intuitive Machines, they're all working on preliminary design contracts for this.
What does that sustained high power enable in a military context that current solar panels can't?
It's all about strategic mobility and resilience in what they call contested cislunar space.
Okay.
Retired Lieutenant General John Shaw coined this term, maneuver without regret.
Maneuver without regret. I like that.
Chemical propulsion is fuel limited. Every time a satellite maneuvers to change its orbit to avoid a threat or reposition, it uses up a chunk of its limited fuel supply. It compromises its mission lifespan.
So that's the sports analogy you mentioned earlier, having an infinite reserve bench. You can swap players, or in this case, change orbits, without worrying about exhausting your resource.
Precisely. With a megawatt-class fission reactor providing power, the satellite has virtually infinite energy for maneuverability. It can change orbit instantly, maneuver aggressively to dynamically avoid kinetic threats, or rapidly reposition for surveillance.
And it doesn't have to worry about running out of fuel.
That capability is priceless in modern strategic competition. And the high power also enables advanced communications and potentially defensive countermeasures.
Okay, so if NEP is the marathon and NTP is the sprint that got canceled, there is one more technology out there that's like the theoretical hyperloop.
You talk about fusion.
Fusion.
Specifically, the groundbreaking work being done by Pulsar Fusion in the UK. They're working on the direct fusion drive concept, which they're calling the Sunbird Migratory Transfer Vehicle.
And this is where we get that 500,000 miles per hour potential that we mentioned at the top.
This is where it comes from. This isn't just splitting atoms, it's combining them.
How does it work? It sounds so elegant.
The ingenuity here is how they manage the output. A fusion reaction naturally generates superhot charged plasma. In most fusion reactor designs, the engineers try desperately to contain all of that plasma to maximize energy generation.
Right.
The direct fusion drive flips that script. It harnesses the typical leakage of that plasma and uses powerful magnetic nozzles to direct it for thrust.
So you're turning waste heat and leakage into raw propulsion.
It's incredibly elegant.
What kind of performance are they claiming?
They project extreme specific impulse, up to 15,000 seconds. The Sunbird is designed as a powerful high-speed space tug, generating 2 megawatts of power.
So what does that mean for travel times?
It means missions to Pluto in 4 years, with no mid-flight refueling required. It needs only tiny amounts of fuel. The engineering risk is, of course, successfully developing the massive magnetic containment systems needed to manage and direct that plasma flow in a controlled way.
But the payoff is a revolution.
A revolution in transit time.
And pulsar fusion isn't waiting around. They're aiming for an in-orbit demonstration of key components as early as 2027.
Yeah. Which brings us to the global competition, because the U.S. is not operating in a vacuum here. This is a geopolitical race defined by megawatts in space.
Okay, so who are the other players?
The other global players are heavily invested in NEP. Let's start with Russia. They are developing the megawatt-class space tug called Zeus. It was formerly known as TEM.
And Zeus is pure NEP, focused on endurance and longevity.
Absolutely. The Russian Keldysh Research Center is deep into developing the core technologies. And the mission plan they published is incredibly ambitious.
What is it?
An uncrewed 50-month continuous test mission to the Moon, Venus, and Jupiter, starting around 2030. They are pushing the operational envelope, claiming continuous operation for up to 10 years.
That 50-month multi-planet test mission is the strategic differentiator.
It is. It proves not just that the system works, but that it can maintain MW power for continuous years in deep space, which is exactly what the U.S. needs to demonstrate with Jetson.
And Russia is strategically teaming up with China on the Moon.
Right. That raises the stakes even further. They're planning a joint international lunar research station, which includes a specific plan to install a nuclear power plant on the Moon by 2036.
So this is about securing sustained power on the lunar surface, especially to survive the brutal 2-week lunar night.
Exactly. And China is also pursuing advanced nuclear power research independently. We know they are looking at those advanced NTP concepts like the centrifugal nuclear thermal rocket to speed up Mars transit once the orbital logistics are solved.
And their lunar plans are equally ambitious. They're using their upcoming Change 8 mission to test early nuclear power systems and something called ISRU.
In situ resource utilization. Basically, using lunar resources. It's a key step towards establishing a permanent presence.
And on the ground, China is already positioned for a massive nuclear expansion by 2050. They're building out the industrial infrastructure that will inevitably support their space goals.
And we cannot forget Europe. The European Space Agency recognized they can't be dependent on the U.S., Russia, or China for deep space access.
So what's their plan?
Their rocket roll study presented a technology roadmap aimed at making Europe an independent deep space actor by 2035, and it focuses heavily on NEP. The nuclear race, fueled by geopolitical competition, is absolutely back on.
So we have this incredible multi-layered technological quest underway. The Americans focusing on military mobility with Jetson, the British pursuing fusion, the Russians and Chinese chasing these megawatt-class space tugs and lunar power. The engineering challenges are immense, but they seem solvable.
They do. Yet, despite all this high-tech ambition, there is a mundane, earthbound constraint that is threatening to stall the entire space nuclear renaissance.
A supply chain problem.
It's a supply chain problem.
And that constraint is the fuel itself. Specifically, this missing ingredient required for almost all of these advanced fission reactors. High-assay Low Enriched Uranium, HALEU.
Okay, so let's define HALEU. Traditional nuclear power plants use low-enriched uranium, or LEU, where the fissionable isotope, uranium-235, is enriched up to about 5%.
Right.
HALEU is enriched between 5% and 19.75%.
Why is that difference in enrichment level so critical for these space reactors?
It's all about physics and packaging. By increasing the enrichment density, you need less total mass of fuel to sustain the chain reaction.
So it lets you build smaller reactors.
It allows developers, whether they're building space reactors like Jetson, terrestrial microreactors, or advanced power plants, to create significantly smaller core designs, have longer operating cycles, and achieve increased efficiencies. It's the high-octane, high-density fuel required for any miniature reactor.
So if the advanced space reactor is the engine, HALEU is the specialized gasoline that lets that engine be small enough to fit on a satellite.
Perfect analogy. And here is the geopolitical supply chain disaster. The United States currently has no commercial domestic supplier capable of producing HALEU at scale.
None.
None. We have government-owned assets that can downblend small amounts from old weapons material, but we lack the commercial infrastructure to enrich uranium between 5% and 19.75%.
That is a staggering national security vulnerability. With all these massive government and military projects, we can't produce the specialized fuel they need.
We rely far too heavily on foreign sources, particularly Russia, for enriched uranium feedstock globally.
How bad is it?
The current geopolitical reality is that without Russian enrichment capacity, there would literally not be enough enriched uranium to supply already operational nuclear power plants in Europe and North America.
Wow.
This reliance means our entire space nuclear future, and frankly our future energy security, is at the mercy of a geopolitical rival.
That single fact redefines the geopolitical risk profile of the entire space race. The technology might be ready, but the supply chain isn't.
And the sources show the scale of the need. Existing U.S.-based enrichment capacity is far short of the projected annual needs for HALEU by 2050.
We're talking orders of magnitude short.
To operate future nuclear capacity, we will require geopolitically secure enrichment services 5 to 10 times larger than what is currently available domestically. This is a vast, immediate infrastructure challenge.
So what is the government doing to fix this, and how quickly can they move?
They are rushing to establish a domestic supply chain through the Department of Energy, the DOE. They created the HALEU Availability Program.
What's the goal of that program?
It's twofold. First, the DOE acquires initial amounts to service immediate government R&D needs and allocates it to promising reactor developers. Second, the DOE aims to jumpstart the commercial market by guaranteeing purchases, allowing private industry to invest in building the necessary enrichment facilities.
And we are seeing that initial material allocation happening now, specifically tying it to terrestrial microreactor development.
Yes. The DOE recently made conditional commitments to several companies. This includes Antares Nuclear, which is developing a 500-kilowatt microreactor intended to go critical by July 4, 2026.
That's soon.
Very soon. They also allocated material to Standard Nuclear, focused on establishing TRISO fuel lines, and Abilene Christian University for their molten salt research reactor.
These aren't primarily space companies, though. They're terrestrial companies.
Right, which proves that the domestic nuclear renaissance and the space nuclear race are inextricably linked by this single specialized fuel source.
So if Antares can't get the fuel for its microreactor...
The Space Force might not get the fuel for Jetson.
Exactly.
The HALEU crisis is a shared foundational problem.
So we have the design concepts for planetary travel, the military need for maneuverability, and the technological pathway to 500,000 mph fusion.
But the limiting factor, the Achilles heel, is still the mundane, earthbound problem of manufacturing enough specialized uranium fuel. The required investment in mining, milling, and enrichment is truly vast.
Okay, so let's synthesize what we've uncovered in this deep dive. The past few years marked a major inflection point for nuclear propulsion.
For sure.
We saw the high-thrust NTP sprinter, DRACO, fail not because the physics was faulty, but because the economics of launch changed due to commercial heavy lift.
And that forced a decisive strategic shift onto nuclear electric propulsion, NEP.
NEP systems are no longer just a hypothetical fantasy.
No, they are now the fundamental necessity for deep space logistics, military mobility, and sustained presence. This applies whether we are talking about the Jetson program providing mission-critical on-orbit power, or using multi-megawatt NEP tugs to move cargo to Mars ahead of human crews.
And that focus also encompasses the next generation of propulsion, the fusion efforts, which share the high-efficiency, continuous thrust profile of NEP, just at a hyper-accelerated level.
It really promises to shrink the solar system.
The race has solidified into a high-stakes geopolitical contest. While the U.S. focuses on securing domestic fuel and developing resilient military NEP, Russia and China are pursuing megawatt-class NEP tugs and planning nuclear surface power on the moon by the next decade.
Nuclear power is clearly recognized globally as the only viable path to becoming a multi-planet civilization.
Now, we've talked about the enormous power involved, so we should briefly touch on the safety framework, which is always the first concern for listeners when we talk about nuclear reactors in space.
And it should be. Safety is paramount, and there is a very clear legal and operational framework guiding this. The 1967 Outer Space Treaty allows for the peaceful use of reactors in space, provided they don't involve weapons of mass destruction.
And critically, all of these planned reactors are launched inert.
Right. Inert, meaning the fuel isn't active until they are safely far from Earth or in a stable orbital environment.
So they only turn them on once they're way out there?
That's right. They are only activated in a safe orbit. This orbit is calculated to ensure that even if the system fails or re-enters thousands of years later, the radioactive material wouldn't threaten the biosphere.
And this isn't brand new policy either.
Not at all. The design safety of these new systems is extremely high, drawing lessons from decades of practice, including guidance even from civilian projects like the new standards in the MIT Maritime Consortium's Nuclear Ship Safety Handbook. The precedent is solid.
So the safety structure is in place, the technology is being matured, the geopolitical competition is fierce. It really comes down to this one core challenge for the West.
It does. The entire journey to Mars and our establishment as a spacefaring species will be defined not by the sheer explosive power of the rocket at launch,
No.
but by the quiet, months-long, continuous, efficient push of a nuclear electric tug. And for that tug to launch, and for all those megawatt systems to function, we first have to solve the seemingly mundane terrestrial problem of manufacturing enough specialized HALEU fuel to power a multi-planet future.
Our ability to establish a sustained civilization among the stars is currently dependent on whether we can successfully build a highly specialized uranium enrichment plant on the ground. Think about that next time you look up.
Indeed.
We've been on a deep dive into nuclear rockets, the quest for interplanetary speed. We'll catch you next time.